Welcome to section 6.3, integration by parts. Our goal today is to solve integration problems using the integration by parts formula. The formula that we'll be using is the integral of u dv equals u times v minus the integral of v du. Now, in order to complete the integration by parts, we will need the following. The product u dv must equal the original integrand, so that will be what we've been given. It must be possible to integrate dv, that way we can find v. The new integral v du, should not be more complicated than the original. This is not the goal. The goal of integrating by parts is to make it easier for us, not more complicated. So if it becomes more complicated, you want to go back and try something else. For integrals involving x to the p, e to the ax, try this. U equal to x to the p and dv equal to e to the ax. For integrals involving x to the p natural log of x to the q, we'll try this. U equals the natural log of x to the p, and dv equals x to the p dx. So those are just some tips that if we see these things, that's what we will refer to. In problems 1 and 2, integrate by parts. Assume that x is greater than 0 whenever the natural log function is involved. Number 1, x e to the 12x dx. Okay. Let's begin by letting u equal x, dv equal e to the 12x dx. Then that means du equals dx, the derivative of x, and v, the integral of dv, is going to be 1 over 12 e to the 12x. Okay, so once we set u and dv, we can find v and du. Now let's substitute these in. Remember, the integral of u dv equals uv minus the integral of v du. That's what we're using. So we have the integral of x e to the 12x dx equals u, which is x, v, 1 over 12 e to the 12x, minus the integral of v, 1 over 12 e to the 12x dx. Okay, so now why don't we simplify? We've got the integral of x e to the 12x dx equals x over 12 e to the 12x minus 1/12 integral of e to the 12x dx. We'll find our antiderivative. So we have the integral of x e to the 12x dx equals x over 12 e to the 12x minus 1 over 12. The antiderivative in this case will be 1 over 12 e to the 12x plus c. And we have found our integral. We wanted the integral of x e to the 12x dx, and that is x over 12 e to the 12x minus 1 over 144 e to the 12x plus c. Okay, the integral of x to the 4th, natural log x dx. Let's begin with letting u equal natural log of x. dv equaling x to the fourth dx, which means du, the derivative of natural log of x, is 1 over x dx. And v, the integral of x to the fourth, is going to be 1 over 5 x to the fifth. Okay, let's substitute these in. We have the integral of u dv equals uv minus the integral of v du. So we have the integral of x to the fourth natural log of x dx equals the natural log of x times 1/5 x to the fifth minus the integral of 1/5 x to the fifth 1 over x dx. So this will give us 1/5 x to the fifth natural log of x minus 1/5 the integral of x to the fourth dx. Now, if we take the antiderivative, we'll get 1/5 x to the fifth natural log of x minus 1/5 times 1/5 x to the fifth plus c. And now we're ready to write our answer of the integral of x to the fourth natural log of x dx equals 1/5 x to the fifth natural log of x minus 1/25 x to the fifth plus c. Problems 3 through 8 are mixed. Some may require the use of integration by parts, other techniques, some may not. Assume that g of x is greater than 0 whenever natural log of g of x is involved. The integral from 1 to 8 of natural log of 7x dx. Let's use integration by parts for this one. We'll let u equal the natural log of 7x, dv equal dx. This will give us a du of 1 over x dx and a v of x. When we substitute these in, we get the integral from 1 to 8 of natural log of 7x dx equals natural log of 7x times x evaluated from 1 to 8 minus the integral from 1 to 8 of x times 1 over x dx. This will give us natural log of 7x times x from 1 to 8 minus the integral from 1 to 8 of 1 dx. So we've got x natural log of 7x minus x from 1 to 8. Evaluating, we will have 8 natural log of 7 times 8 minus 8 minus 1 natural log of 7 times 1 minus 1. And this will give us approximately 23.257. The integral of 9x e to the x dx. Let's use integration by parts. We are going to do u equals 9x, dv equals e to the x dx. That means du, derivative will be 9 dx, And v, the integral of dv, will be e to the x. So if we substitute that in, we have the integral of 9x e to the x dx equals 9x e to the x minus 9 integral e to the x dx. This will give us 9x e to the x minus 9 e to the x plus c. The integral of 3x to the 5th e to the x to the 3, or e to the x cubed dx. I'm noticing there's a typo. Use integration by parts on this one as well. U equals x cubed, and dv will be the 3x squared e to the x cubed dx. And what this will give us is du will give us 3x squared dx. V will give us e to the x cubed. So now we have the integral of 3x to the 5th e to the x cubed dx equals x cubed e to the x cubed minus the integral of e to the x cubed times 3x squared dx. This will simplify to x cubed e to the x cubed minus e to the x cubed plus c. For e to the x to the 4 4x plus 3 over e to the 4x plus 3x. Our u substitution here would be u equals e to the 4x plus 3x. Our du would be the derivative, so 4 e to the 4x plus 3. And here we're just using substitution method. So let's see, we will rewrite this as the integral of 1 over u du. That will give us the natural log of u plus c. And if we plug back in our u value, we have natural log of e to the 4x plus 3x plus c. So if you see our substitution method come back where I see a function and I see the derivative, I can use u substitution. You don't need to use integration by parts. The integral from 0 to 2 of x e to the 2x squared dx, let's use u substitution on this one. So we'll let u equal negative 2x squared. That gives us a du of negative 4x. So if we substitute, we'll have negative 1/4 times the integral from x equals 0 to x equals 2 of e to the u du. And this will give us negative 1/4 e to the u evaluated from x equals 0 to x equals 2. And when we evaluate, well, we have to turn it back into u's before we evaluate. Negative 1/4 e to the negative 2x squared from 0 to 2. Now we can evaluate, so we have negative 1/4 e to the negative 2 times 2 squared plus 1/4 e to the negative 2 times 0 squared, which gives us an approximate value of 0.2499. The integral of x plus 7 to the 8th times x minus 3 dx. Okay, this one will go back to integration by parts. So I'm going to let u equal x minus 3, dv equal x plus 7 to the 8th dx. So this gives us a du of dx and a v of 1/9 x plus 7 to the 9th. Let's substitute that in. So we have the integral of x plus 7 to the 8th times x minus 3 dx equals x minus 3 times 1/9 times x plus 7 to the 9th minus the integral of 1/9 times x plus 7 to the 9th dx. If we simplify a little, we'll have 1/9 times x minus 3 times x plus 7 to the 9th minus 1/9 times the integral of x plus 7 to the 9th dx. And then when we find our antiderivative, we have 1/9 x minus 3, x plus 7 to the 9th, minus that 1/9 times 1/10 x plus 7 to the 10th plus c. And so this integral of x plus 7 to the 8th times x minus 3 dx equals 1/9 x minus 3 x plus 7 to the 9th minus 1/90 x plus 7 to the 10th plus c.